Can you hear me? Okay. So, um, my name is Aishah, and today I'm going to do your A-level physics session on optics. So, what we are going to cover today is going to be refraction and its related concepts like real depth, apparent depth, critical angle, total internal reflection, water droplet prisms, and if we have time, we can do practical 16 as well. If I'm lagging or something. So, before I start, so let me give you, I was asked to say a few tips on what to do in the last few days of for exam preparation. So for the 2026 batch, who are going to sit for the exams, I would recommend you guys to start recapping everything you've done so far, like go through all the theories as well as do the past paper questions from, if you want, like if you're like already very good at what you're doing, then maybe like 2010 onwards would do. But then if you have someone who has done any past papers, haven't done past papers like as much, I would recommend doing 2019 onwards. So yeah, materials like all your theory. So as for 2027 and 2028, if you uh, if you go along with your theory, if you start doing papers along with your theory, I think it could be sufficient. So for 2027 people, if you haven't started studying, I think it's like high time for you to actually start. Before it's too late. So one thing Twenty 27 and 28 batch to do is to have a particular book or something. Would all have the tute printed out. Can you hear me now? Is it still lagging? I'm so sorry about the delay. Uh, let's continue. So, as I was saying, I hope you guys have printed the tute and it's ready. So, let me start screen sharing and then we can directly jump into the lesson. Okay. Is the audio better? Okay. And you can see the screen as well, right? Okay. So have your tutes ready and then I'm going to start the lesson. You can fill it along while I'm teaching as well. And I'll give you some time in the middle. It depends. So uh, I'll start now. So the main topic today is refraction and all the related concepts like real depth, apparent depth, critical angle, total internal refraction, and there is a small part about water droplets, about prisms, and if we have time, we can do practical 16. And then in the middle, I'll do some past paper questions as well. So refraction, if you take the topic refraction, it's a property of a wave and it can take place in any wave like sound, water, light, or anything like that. But here we are going to focus on light. So when a light ray or a beam of light moves from one particular medium to another, refraction takes place. So about light, it's an electromagnetic wave, and I hope you all know about the electromagnetic spectrum. So it has radio waves, microwaves, infrared, visible, UV, X-rays, and gamma rays. So in that spectrum, light rays are also included. So the main thing behind all these concepts is going to be the wave equation. That is C equals F lambda. So this equation is right here. So you can write this equation in that box that's given in your tute. So C equals F lambda. And this equation, C denotes the speed, F the frequency, and lambda the wavelength. So frequency in this equation is going to be constant, and according due to the constant frequency in any medium, doesn't matter if it's glass, water, air, so it's always going to be constant. So because the frequency is constant, the speed is going to be directly proportional to the wavelength. So as you can write this as well. So the speed in air is going to be 3 into 10 to the power 8 ms minus 1. So this is the speed in vacuum actually. So vacuum is like it doesn't have any what do you call particles. So it's like empty. And in vacuum, the speed is 3 into 10 to the power 8 ms minus 1. So it's approximately equal to the speed in air. So we consider it as equal. So in other mediums other than vacuum and air, the speed in other mediums is going to be less than 3 into 10 to the power 8 ms minus 1. So now we know that the speed in each medium is going to be different. Like from one medium to another, the speed is going to change. Because of this change in speed, the path that the light moves is also going to change and it's going to bend according to the speed of the light. in that particular medium. So why it happens? Why does it have to bend? So usually, speed, you just slowing down of a light ray doesn't actually do anything. So reason why it changes, I'll explain it like the behind the scenes of what actually happens when a light ray is being refracted. So where is this? Okay. So we all know that if you when you draw a wave, it's going to be something like that. Yeah. And we know that this is going to be the crest. This as well is going to be a crest. And the distance between two same positions in a wave is going to be the wavelength. So we know in a wave there is crest and throws, and then like a wave moves in a particular direction. Now, when you speak about light rays, it's an electromagnetic wave, which means in addition to this wave, there's an electric field as well as a magnetic field, which is perpendicular to this. So now if we consider multiple waves together like this, and then you align, all the crests are aligned. Draw another wave. All of these crests are aligned, and you see it like this. It's like the top view, like when you look at the wave from above, you see like these straight lines, and these are called wave fronts. So if I consider one such wave front like over here, and I represent it by these small circles. I know it's not small, it doesn't even look like circles. Okay. So these, just think that each of these wave is going to uh, enter this glass. So this is the glass. This thing is the glass. So it's going to enter this glass. And then there's also another thing that I want to tell you, that the direction of the wave is always perpendicular to the wavefront. So that's going to be like that. So perpendicular, the direction of the wave is perpendicular to the wavefront. So like this. So for y'all to understand better, there's a animation here. So basically I just took it from YouTube. So I'll show it to you all. Is the video playing for you? Okay. So if you look at this animation right here, so these are the um, what do you call, the waves that I mentioned earlier. And then this, when it enters the medium of glass, we know, we all know that the speed in a glass is going to be less than in air, as I mentioned earlier. So the speed is going to, of these waves are going to be slowed down. So if you see, and in this, at the same time, the other waves over here is going to move at the same speed it initially moved. So if you see this, these move in the same speed, while this particle that just entered is going to be moving in a speed which is going to be less than the others. So now the second wave is also entering at this moment. This particular particle is also going to be moving at the same speed as the one below. So it's going to enter, and similarly you can see the bending of the wave, like let, when it enters more into this, into the glass. So there was another thing that I told y'all about the direction of the wave being perpendicular to the wavefront. So now this thing is the wavefront, and the direction of the wave is going to be like that way, perpendicular. So it's going to strike the glass at this particular point here. So now if you draw the wavefront inside the glass, it has changed direction like this. So I'm drawing multiple wavefronts actually. Yeah, so it's going, the direction of the wave inside the glass is going to be perpendicular to the wavefronts inside the glass. So that's going to be looking like that. Now, as you see, we have seen that the pathway, instead of going like straight like that, the light ray has actually bent inside this medium. So that is how, um, according to the speed, the light ray changes the direction. So that's the theory or the reason behind this. So if you guys want to note it down somewhere, you can write it under, there's a my notes section inside in the tute. So you can write it under that, or whatever you feel is important, you can write it there. Then moving on. If you guys need time, please let me know, okay? You guys need time? Okay. So I'll give you like 2-3 minutes. You can write it down. Like whatever you remember about what I told you. So this actually helps you all recall everything better. So once the session is over, I'll send you the presentation on the group. So if you miss any point or if you want to go through it again, you can refer it and go through it. And by the way, did you all understand the concept as to why the ray bends? Can you all like give a thumbs up or something if you all understood? You are done writing, right? And let me know that as well. Maybe with another emoji. Okay, so I'll move on with the lesson. So in this part, we are going to learn about the parts of the rays, or like how do you name the rays. So this is the incident ray, as mentioned. Incident ray is the ray that goes and hits a boundary between two different mediums. So, and the ray that emerges, or the ray that comes onto the other side of the medium, is going to be the refracted ray. And the line that is perpendicular to the surface, or the boundary between the two mediums, is called the normal. So this normal is perpendicular to the boundary. So we know the light ray, it bends towards or away from the normal depending on the medium. So the what you guys can do is like, you might have this question, what direction does it actually bend based on the medium? So I'll tell you a small thing that I used. So now if you consider this as the road, let's say this is the road, yeah, and then there's a vehicle there. There's a vehicle there and it's entering the medium, and this is like a place where there is a mud or something. So this particular vehicle, it moves along a road and it's going to enter this muddy place. Okay. So first we notice that when the vehicle enters, this particular wheel that's there enters first, and then the other wheels enters. And then what you do, you all know that we start accelerating, right? And then, since the force is more from this side, this particular side, and the force from this side is less because only one wheel is out, and here this side there's two wheels out, this particular vehicle will start turning towards the middle line. So in this case, a normal. So this road, you can consider it as a rarer medium, and then the mud here is going to be the denser medium. So that is one way you can remember which way the light rays can bend. So you guys must be having like other ways you can remember it easily. So this is one such way. So now if you consider this rare medium, like I said, example road. From the word itself, you can figure out that the particles in this medium is going to be like scattered all over, and denser medium, like we learned when we were in small grades. So it's going to be tightly packed and all of those. So that is why like there is more space towards and away from the normal. You can remember that way as well. So in summary, the light rays bends towards the normal in a denser medium, and it bends away from the normal when it enters a rarer medium. So there's always a denser medium and a rarer medium. So there is another thing that I want to say. If the light ray travels along the normal, the incident angle and the refracted angle is equal to 0. So the angle that is made between the incident ray and the normal is called incident angle, and the angle that is made between the refracted ray and the normal is called the refracted angle. So if I as well as r in this case is equal to 0, it moves along the normal and there is no deviation. So this is one instance, like an example. Okay. And then there is one other thing I have to tell you regarding this. When you reverse this, the ray, let's say this ray, it initially moves in this direction. Along the same path, if you reverse the ray in the opposite direction, the light ray will travel through the same pathway. So it will be when a refracted ray is reversed, it goes through the original path. So that is the other point. So then we have some videos on, before that, I have a question to ask. So this light rays usually in, let's say, a glass block, a light ray passes, but you can't even see it. So can someone tell me like one way where you can actually visually see a light ray moving from one medium to another? Like one thing that you can use to see it visually. Okay, so someone has sent an answer and it's correct. So it's laser. So when you shine a laser beam through a glass block, you can actually see the pathway that the light ray moves. So if I show you the video, you can see this is also something I got from YouTube, obviously. Um, okay, so in this case, if you look at this, you can see that the light ray bends, you can visually see it. So yeah, so that is how it is represented. Like you can visually see a method, you can see it. Then moving on. So there is another thing that I want to tell you. When refraction takes place, in this case, we can see refraction taking place. So let's say this is the incident ray. I marked it, incident ray. And then this is the refracted ray. At the same time, we can see this tiny beam over here. It's being reflected back into the same medium. So whenever a refraction takes place, a small amount of light rays gets reflected back into the medium as well. So this is, I think there are like two past paper questions using this concept. So a small portion of light rays reflect back into the medium although there is reflection. Okay, so if you look at this is like a funny image that I saw. It also has refraction taking place. So that's why you see the polar bear splits into half and like half the body is somewhere else. Then, okay. So now we're going to like the serious part of the lesson, and it's going to be boring because it's about laws of refraction. So in the tute, I'm named laws of refraction, and you can summarize what I'm saying. Like you can draw it on the diagram while I'm saying, or after I say, or after the class as well. So regarding the first law, it's just a bunch of words that describe an image, the image that's given here. So basically, they are saying that incident ray, this particular ray right here, this ray, refracted ray, as well as this normal, meets at a particular point on the same plane. So the plane is going to be this boundary, and this point, the point of incidence. So that is the first law. It's like very easy. You can remember it like in few minutes as well. So incident ray, refracted ray, and normal are at the same point, are like meeting at the same point on the same plane. So the next part is the second law. So this is the important law out of the two. So in this law, it's also called as Snell's law because a particular person called Snell, he came up with this and then he said the sine angle or the sine value of incident angle, this particular angle, the angle between normal and incident ray, and the ratio between the sine I as well as the sine of the refracted angle is going to be equal to the refractive index. Now, this refractive index here is a constant. So, this constant, it depends on two mediums. Like in this case, if you see in the image, air and water. So, it depends on this. So, refractive index for air water medium is going to be a constant. Now, if you take glass and air medium, the previous example, that is going to have a different value for refractive index. So that is about this law. You can write this equation sin I divided by sin r equals n. You can write it in that box that's been given in your tute. Then we can go to the next part. So next we have a question. I know it's been boring for y'all, like listening to me talking for the whole time. So y'all can, I'll give you like few minutes to try out this question and send me your honest answer because I've already marked the answer in this. So yeah, let me know if y'all actually got the answer. You can like send a message in the chat or you can react or something like that. I'll give you like 2 minutes. I hope it's enough because it's actually easy. Okay, so I've got some answers. And let me explain, and then you can check if you actually got it correct. So, so in this, they're saying there is this particular rod that's been connected, and above the surface there is 1 meter, and below the surface of water there is 1 meter, and that the sunlight falls on the rod, making a 45-degree angle. So one thing about 45 degrees is like they've shown it here, but we know it's parallel. All these rays are parallel. So the angle that's going to come here is also going to be 45. So if that's 45, the angle here is also going to be 45. Okay, something about 45 degrees, a triangle with 45 degrees, as we all know, it's an isosceles triangle. So the length here is also going to be 1 meter. Yeah. So till there, I think everything is clear. Then comes what we learned about refraction. Now we know air, that means this medium, I'm going to write it as air, is having, it is a rarer medium, while water is much denser than air. So same like that road situation I said earlier, this light ray is going to be bending towards the normal. So it's going to end up like here. So if this is 1 meter, like over here, like highlighting it, this is also going to be 1 meter, but this normal falls here. If this image was to be 2 meters, the light ray will go like that. And then this is going to be 1 meter. But it didn't go that way because it cannot move in the straight path because of the refraction that takes place. Because of that, the length of the image is going to be less than 2 meters. So this is 1 meter, and this is also 1 meter. So it's going to be less than 2 meters, but it's going to be greater than 1 meter. So that is going to be answer 3. And some of you all got those answers. So I hope you all understood how that came. If you all understood, please drop a thumbs up or something like that. I think it's easier for you all to react than send a message in the chat. Okay. Then moving on. Okay. So we are going to move on to more about refractive index. So although the presentation is arranged like this, it looks empty. I'm going to do a lot of writing. So I think you all can parallelly write it in your tute as well. So here, first I'm going to talk about absolute refractive index. So if you look at this equation, so Nm is the refractive index of a particular medium. So M there means medium. I just wrote it for you all to understand. So Nm, refractive index of a particular medium, is equal to the speed in vacuum. So C here is speed in vacuum, speed of light in vacuum, which is 3 into 10 to the power 8, as I said earlier, divided by the speed of that particular light ray in another medium, or let's say glass. So refractive index of glass is going to be the speed of light in vacuum divided by the speed of light in glass. So we know speed in any medium other than vacuum, so right here, is going to be less than the speed in vacuum. So Because of that, the denominator here is going to be very low than the numerator. Because of that, we are going to get Nm, that means refractive index of a medium, as a positive value and like a greater value than 1. If you are to get 1, then the particular medium should be C over C. So that's going to be vacuum or air in itself. So here, main thing you can understand is any refractive index is going to have a value greater than 1. It cannot be equal to 1. It has to be greater than 1, because the refractive index of 1 belongs only to vacuum or air. So like if you do a question and you come across refractive index 0.5, you definitely know that you're wrong. So knowing this also can help when you're doing questions. So that is about absolute refractive index. So absolute refractive index is the refractive index of that particular medium compared to vacuum or air. Then moving on, I'll do about relative refractive index. So relative refractive index is when you compare the refractive index of one particular medium to another medium. So let's say glass and water, or glass and air, or water and air, or something like that. So you're going to compare two different mediums. So if you look at this, it's 1 and 2. So basically, you actually write it like it comes as a subscript, but I couldn't find it. So 1 and 2 or something like that. You actually read it like the refractive index of second medium with respect to the first medium. So refractive index of the second medium with respect to the first medium is a relative refractive index. So it's represented by this symbol. So if you look at this refractive index of second medium with respect to the first medium. So the refractive index of the medium that you want is like on the numerator, and what you're comparing it with is coming as a denominator. So that is there. So now we are going to see how to derive this particular equation. So how you derive this equation is, we know that speed is directly proportional to sine I. So this was not said by me, it's said by the guy who found this, okay? So you can't blame me for all these derivations. So it's sine R. So since this is directly proportional, when you divide this particular equation by this, you're going to, it's going to, both sides are going to be equal. So that's going to look like this. Please excuse my handwriting, it looks ugly. So that's how you get this part. Now we all know we can write this. I'll write it and show, and then you tell me if it's correct or wrong. So you can write C over C2 divided by C over C1 is going to be equal to sine I divided by sine R. Okay, let me know if this part is correct. Like, is it correct? Reply yes or no. Okay. So this is actually correct. So once you simplify this, like C over C2 and C over C1, when you simplify this, you actually get this equation C1 over CO2. So that's how you get this. Now we also know that speed in vacuum divided by a speed in a particular medium is going to be equal to refractive index. So C over C2 is actually N2. So it's actually N2. And C over C1 is actually N1. That is equal to sine I divided by sine R. That is how you get this equation. So if you want, you can write it down. This derivation is not important, but it's there in your syllabus. So it's better if you know. So that's how you get this. If you all are done writing, you can react or something or send me a message in the chat. You guys are done? I got one message. Okay. If I'm too fast, let me know. Like if I'm moving on with the lesson too fast, so I can slow down. So now we are going to see how we are going to derive equations for absolute refractive index. So the important equation in this is going to be this one right here, the one I'm circling. And the one I wrote earlier, which is N2 over N1 equals sine I divided by sine R. So based on this thing right here, you can cross multiply and you can get a one single line as N1 sine I actually is equal to N2 sine R. So that is the main equation there. Now with this thing right here, I'm going to show you how you can derive more equations. So in this, there is C over C2 and C over C1. Now we know we can cancel off the speed of light in vacuum. When you cancel off the speed of light in vacuum, you get C1 over C2. That's going to be equal to N2 over N1. Like when you get it from the previous part. So from this, if you get, when you cross multiply, you can say N1 C1 is equal to N2 C2. Or if C is too confusing, you can use V1, V2. Yeah. And then we also know that C here is equal to F lambda. So F lambda 1 divided by F lambda 2 is equal to N2 divided by N1. And frequency, you can cancel it off and you can cross multiply. So that is n1 lambda 1 is equal to n2 lambda 2. So these are the two equations that you need when you're doing questions. So you can write these two equations also down, and you can let me know once you're done, or yeah. Okay, so I'll move on. So now there's a bunch of questions that you guys can attempt related to the equations that we derived, like the equation we derived last actually. So you can try these too. You can take like 2 minutes. Thing is, it's very easy. Direct application of the equations that I'm erasing right now. So yeah. And please reply in the chat if you understood or no or anything like that, because I don't know whether y'all are actually sitting there or sleeping on the bed or something. I think most of y'all are having dinner now, right? I give y'all a break about around 10 minutes. Not now, but like in a little while, probably. You guys can send the answers in the chat, like consecutively or something, because that's two questions. Okay. I'll start with the first one. It's the easier one because it doesn't have any values. So you can do it faster. So they are asking us to find the speed as well as the wavelength of the second medium. So we know the first medium, the speed is V1, V1. Refractive index N1. Um, Second medium, speed is V2, refractive index N2. So as we know, N1 V1 is equal to N2 V2. Regarding speed, if you subject V2, you can get N1 V1 divided by N2. So you can eliminate the answers, this fourth one and fifth one. Yes. Then the next part, it has a similar pattern, the equation for wavelength also. So N1 lambda 1 is equal to N2 lambda 2. And now you have to subject lambda 2, and then it's going to be N1 lambda 1 divided by N2. So that is going to be your third answer. Similarly, if you apply numbers to the next question, like in the equation, you can get the answers for the other question 17. So these are two consecutive years that has come at the same question number. So in every year, there is one part, one question, MCQ question from whatever I'm teaching today. And there's another question on lenses and all of that, MCQs. Usually it's like that. And then one practical on and off, because it switches with waves lesson as well. So regarding this question, now they're asking us to find the velocity and the wavelength of a particular medium, while the velocity and the wavelength of light in vacuum is given. So if you consider N1 V1 equals N2 V2, as I said earlier, the velocity, the refractive index in vacuum is going to be 1, and the speed 3 into 10 to the power 8 is going to be equal to N2. Now here the refractive index is 1.5. You can write it as 3 over 2. It helps in the calculation because it's easier. Then you can cancel off the 3, and it's 2 into 10 to the power 8. So that's V2. Yeah, I hope you all understood that. So similarly, you can find lambda value as well. So N1 lambda 1 equals N2 lambda 2. N1 here is 1 and lambda 450. So this is in air, 450, and the refractive index is 1. That is equal to 1.5. The refractive index in another medium, you can write as 3 over 2 for ease, and then lambda 2. When you simplify this, you get the value for lambda 2 as 300 Newton meters. So that is going to be option 3 again. So that's how you do this question. It's not very hard at all. I mean, it's not hard at all. Not even hard. So you can do this in few minutes. I think even 1 minute is enough to do one of these questions. So that's how you earn time when you're doing past paper questions. So you can do it in your mind as well. Especially this first part, you can just think of the equation, subject it in your head, and then you can get the answer. So that's how people who get really good marks actually think. They don't write much, especially like the people who get good island ranks. Okay. Then moving on. I think we have more questions. Let me check. Yeah, we have more questions. So the first question there, I'll do it and you guys can listen. So when a light wave traveling in a rarer medium enters a denser medium, they're asking which of these properties changes and which of these properties doesn't change. Now we know the wave equation, C equals F lambda. Their frequency is always constant. It doesn't matter what medium it is in. So frequency is constant. So in this, there is no such explanation as frequency is constant. I think fifth one has, but the second part of this question is wrong. So if you take that, we know that velocity and speed and actually velocity and wavelength are actually directly proportional to each other, and these two properties changes when the medium changes. So here the answer is going to be answer 4, where both velocity and wavelength change. Then the next question, I think you guys can try that. It's actually easy, based on absolute refractive index. So you just have to divide the refractive indexes and find. But you should remember which refractive index comes in the numerator and what comes in the denominator. So most people actually confuse this part. I was the same. So I actually memorized the equation. I'm like, this should come up, this should come down. And then I do the question. So yeah, I give you like 2 minutes. I think it's more than enough. You can try. And please do reply in the chat. You all are like, I'm like speaking to a wall or something. Am I like moving too fast? Can you all reply in the chat for that message at least? Okay, so moving on. About this is the relative refractive index. So they're given the refractive index of water as 4 over 3 and glass as 3 over 2. Oh, what happened? Okay, as 3 over 2. And then they've asked the refractive index of glass relative to water. So they're asking the refractive index of glass with respect to water, which means it's like N refractive index of glass here and water here. So that's going to be refractive index of glass divided by refractive index of water. Then you can substitute this refractive index of glass 3 over 2 divided by 4 over 3. But some people, since glass comes on the numerator, you just read the first number as that, as like the first number they're given as glass, and then you switch the numerator denominator, and then you get an answer which is totally upside down of the actual answer. So once you simplify this, you get 9 over 8. So this is how you do this question. So always read carefully, mark everything so that you don't miss on these tiny details. So usually people who are like me especially usually make mistakes in stuff that are very easy, like they miss these tiny parts. So you have to be very attentive when you're doing these questions. Then we got, so the next part of this lesson, I'm going to explain more on how to attempt MCQs and the points that are usually questioned in MCQ. So that is called MCQ points. So in your tute, there is a part called MCQ points. I think you can see that in your tute. So under MCQ points, you can start with this. Okay. So these are the points related to this concept that I would consider as very important, especially the first one. So the first one, it's something that it should click in your head as soon as you see the question or any question in general. You should know that the rare medium has a lower refractive index. So that's the main point. Rare medium, the one which, example, air or vacuum, it has a rare medium, um, and that has a very low refractive index. So that is one point. And then I will do a question which proves how important this particular point is. So the second point here, I already mentioned, refractive index of any medium is going to be larger than 1, and the speed in vacuum is always greater than the speed in any other medium. So this is like, if you go wrong in a question, if you get refractive index less than 1, you can double check your answer because it's not possible. So one other point that I found in a book actually is that when you take the refractive index, if you multiply it in this way, like refractive index of the second medium with respect to first medium into refractive index of third medium with respect to second medium, will give you the refractive index of third medium with respect to the first medium. Okay, it might be like a tongue twister or something. So I'll just show how it actually comes. So we know refractive index of second medium with respect to the first medium is n2 divided by n1. And that is, when you multiply, it is going to be refractive index of 3, n3 divided by n2. And then you can cancel n2 and you're going to get n3 over n1. So this is refractive index of the third medium with respect to the first medium. So there is one such question here. You can take a screenshot if you want. Here they've given the refractive index of each individual medium. And in the end, they're asking the refractive index of paraffin with respect to water. So what you're going to do is find, they're giving you a bunch of steps. First, you need to find glass relative to water, then paraffin relative to glass, and then you can multiply in this similar way, and then you can get the refractive index. So basically, it's like an example to show where you can actually apply this. Then regarding the last point here, refractive index of second medium with respect to the first medium can also be written as 1 divided by refractive index of the first medium with respect to the second medium. It's like a reciprocal basically. So that is for those MCQ points. And now this question is actually related to the first point. So the first point was, in a rare medium, the refractive index is going to be the lowest. Okay. You can try this question in like 2 minutes. and reply back. Send it in the chat. Send your answer in the chat. Okay. So here, as I said, rare medium is going to have a lower refractive index. So rare medium refractive index is low. Another thing we know about rare medium is the ray bends away from the normal. So away from the normal. Away from normal. So one way you can do this question is by looking at the pathway of the rays. The ray which is more away from the normal, like most away from the normal, is going to have the lowest refractive index. Now if you look at this, we know that actually C is going to have a refractive index which is very low because of the it moves away from the normal more than in any other medium. So C is going to have the lowest. If you see that way, you can eliminate option 3 and option 5 because C is not the lowest. And if you look at the diagram again, you can find the highest refractive index. It's going to be a denser medium and the ray is going to move very close to the normal. Now, if you look at D, it is very close to the normal, so the refractive index is going to be very high. So in that case, you can eliminate option 4. Now here you will be tied with 2 answers, and then the difference between this is the refractive index of A and B. Now if you look at this A and B location here, we find that B is more denser than A. Denser medium has a higher refractive index. So higher the refractive index, it has a higher refractive index than A. So you're going to get answer 1 there. So that is how you do this and how you apply the first MCQ point that I told you about. I hope you all understood this, and if you did, please send the message in the chat. Or if you didn't understand, I can repeat it again. I hope you all understood that question. So moving on, uh, whoever is sending messages, please send it to the message that to the account that I'm speaking through. I won't be checking the one that is like the screen is shared through. So the one that I'm speaking through, you can drop the message through that. I forgot to say that before. I'm sorry if I ignored your messages earlier. Okay. So moving to the next part. So this is about apparent depth, real depth, all of that. So this is the main equation in this concept is going to be real depth divided by apparent depth is equal to the refractive index. So here it's refractive index of medium B with respect to medium A. In this case, you should always remember in the refractive index, the first medium, the one that I'm circling right now, the medium A, that is the medium where the observer's eye is in. So do not confuse. The eye of the observer is in the medium that is being mentioned in the first. So it's medium, second medium with respect to the first medium. So in the first medium, the observer's eyes should be there. So that's when this will actually work. And we also know that refractive index is a constant, as I mentioned earlier. So because it is a constant, when you put it in a graph, let's say here real depth, I'll take it as R, apparent depth as A, the gradient is going to be a constant y equals mx graph. So usually they don't question about this graph. That is bet like you can, it's nice to know. Okay. So in this situation, what most people miss is that you can use this equation when observer is in the denser medium or when the observer is in the rarer medium. So let's say now if you look at this image, this child is looking at the fish and the fish is he sees the fish. So we know this is air, and then this is water. Because you know that this particular child here is in the rarer medium and he observes the denser medium. At the same time, this fish here is in the denser medium and he observes this child in the rarer medium. So this equation can be applied in both situations when the observer is either in the denser medium or the rarer medium. But one thing you should keep in mind is this, let me highlight it there. So this thing A there, in that medium is where the eye of the observer should be. The first medium that is there in this equation. So this is also equal to NB divided by NA. So in this case, the eye of the observer should be in the medium of the denominator. So now if you look at this diagram, it's from the resource book actually. So if the object is here and you draw two light rays, so this is one such light ray, it's going straight, no deviation because it's perpendicular to the normal. And the other ray is moving like this and then it gets refracted and it goes into air. So now if you trace back this refracted ray, right here, it comes and meets at a particular point at the refracted ray right here. And at this point, you can get the image.
So now in the tute, you can write the equation real depth divided by apparent depth is equal to refractive index. Then in the image, now this is how the image is formed. You follow the refracted ray, you trace it backwards, and at the point where both the refracted rays meet, that is going to be the place where the image is formed. So that is regarding this. Now, okay. Now I'm going to tell you what real depth and what apparent depth is. So everyone know real depth is the depth from the surface to the depth of the object, till the depth of the object. The apparent depth is the depth that you actually see. So the depth from the surface till the image. So that is apparent depth. So the ratio between real depth and apparent depth gives you the refractive index between these two mediums. So here medium A and medium B. So yeah. And the amount by which this image has shifted, like than the object, it has moved more above and the depth is less. This distance is called apparent shift. Okay. Then so that is about the equation and how you mark it on this diagram. So in your diagram on the tute, you can mark real depth, uh, apparent depth, as well as the apparent shift. So now here there is a video here. So it's like I'll show you the first part of the video. After this person starts teaching that I don't even understand what he's teaching. Something else. I think it's not relevant. So I'll just show you the beginning of the video. It looks like an optical illusion actually. So, okay, so this person pours water and the coin that initially wasn't there starts to appear. So that is because of this real depth, apparent depth concept. When you add water or when there is another medium, the image of that particular object is actually seen as if it is lifted. So explaining the theory behind this concept actually. How the equation or how you derive the real depth, apparent depth equation. So we know the refractive index of B with respect to refractive index of A, you can write NB over NA. That is equal to sine B divided by sine beta divided by sine alpha. So beta the angle here and the alpha the angle here. So if you consider just sine values, you actually can't do this, can't derive this. It's like more for maths people. So how we actually derive is you approximate the sine alpha value and sine beta value to their tan values. So everyone knows sine, cos, tan, I hope. So that one. So if you take tan alpha, this equation will actually be tan alpha divided by tan beta is equal to NB divided by NA. So you can write this down in the side, like under the topic, like how it actually comes. Then we know the tan alpha value. So if this is alpha, is like alternate angles. This is also alpha. It's a lot of O-level stuff. So if you're 28 batch, and you did your science well, this is it can be easy. So sine alpha is opposite over over hypotenuse. So opposite over hypotenuse is sine alpha, but here we are looking at tan alpha. So tan alpha is opposite over adjacent. So opposite of it's going to be AP. The adjacent one is going to be PO actually, because the object is there. So this is the adjacent side of tan alpha. That is going to be divided by tan beta, which is going to be AP divided by PI, which is also equal to NB divided by NA. And then you can cancel this off, and then you get PI. Yeah, you get that. And once you derive it, we know that IP value, IP is the value, is the apparent depth, and OP is going to be the real depth. So once you simplify it, I think I switched the numerator and denominator. So it's going to be it's sine beta divided by sine alpha. So it's going to be tan beta divided by tan alpha. I'm sorry. So it's going to be AP over PI in the numerator and AP over PO in the denominator. And when you simplify, you get OP divided by AP. That is real depth divided by apparent depth, IPA. So OP is the real depth as you see in this image, and IP is the apparent depth, the depth you actually see. It's going to be real depth over apparent depth, and that is going to be equal to the refractive index. So this is about all of this. So that's how you derive that equation. So these derivations, it doesn't come, but it's there in the syllabus as to how it has come in your resource book as well. So it's safer to know it, especially if you're 28 batch or 27 batch, because you're still in the beginning. So it's better if you know the background story of how it actually came. Then the next one. So this is about, like, when you put a pencil in water. You can try it at home if you want. You can see. I'll explain this directly because it's a bit different. So the image you, oh, about the previous one, did you all understand how it was derived? Like the derivation of uh, the real depth or apparent depth equation? If you all did, please reply in the chat. I'll continue, you all reply. Then when you put a pencil in water, we can see that this part here. So we are not focusing on this part, we are focusing on this. It is more lifted than uh, in air. So it is more lifted than when it is in air. The concept behind this is, I'll draw it and show you. So if this is your water glass and this is the water, and you dip your pencil, let's say this is the normal way. Same like earlier when I drew the light rays that I drew one like this and the other light ray like that, and then it gets refracted like that. where both this refracted ray extends and meets. That's the point where the image is formed. If the image is formed there, let me. Okay, so image is formed here. And then, similarly, each point of this rod or pencil or whatever, it meets at a particular point, and you get the image of this entire point like this. It's more lifted than it actually is. So this is how you actually see. Like you don't see it as a straight, it looks like it's broken. So that is the image that you see. So now we know, compared to air, if you put it in a medium, it is more lifted. Now we know, in air, the refractive index is 1, and the refractive index in any other medium other than air is going to be greater than that. And here they're also saying Na is greater than Nb. Let's say the refractive index of Na is 2. If the refractive index of Na is 2, then Nb is going to be less than that, but still greater than air. So that's going to be 1.5. Now I said when you dip a pencil or a rod into water or any other liquid, it's going to be lifted. If you look at option 2, it is more bent, so you can eliminate that. And 3 as well, it's not lifted. 4 also, it's not lifted, it's more going more downwards. But in 5 and 1, you can see it's lifted than when you compare to air. But we also know, so here refractive index of A is 2 and air is 1. So higher the refractive index, the more lifted the object is going to look. So you can get another MCQ point from them. When the refractive index increases, the image looks more lifted. Like in this case, the pencil is more lifted. So now if you compare Na and Nb, Na is going to have a higher refractive index of, like in this case I've given 2 and Nb as 1.5. So it's going to be appear more lifted in A than in the medium B. Now if you look at this, you can see it's true, right? B, it is more bent downwards than it is in A. But in the fifth one, in B, it is lifted. So fifth one is also wrong. The answer here is answer 1. So I hope you all understood. If you all understood, please drop a message. I got one message earlier saying they understood. What about the others though? Some of you all are just existing. Don't even know what you all are doing. Okay. Reply in the chat if you understood that. Fatima, which question didn't you understand? Or which concept? Is it this? Like the previous one that I did? Okay. I'll explain it to you again. So, this laptop is glitching actually. Okay. So this question, as some of you all didn't understand, I'll explain it again. So we know if you dip a pencil in water, I'm referring to this circled one here. So that point, if you look at that point, it looks like it's more lifted in the liquid than it is in air. So when you dip a pencil in water, it appears to be more lifted than it is in air. Okay, did you all understand that part? Okay. If now we know it's lifted in the medium than air. Now we know air, the refractive index is 1, as I mentioned earlier in the first slide. I think second slide, okay. And if you consider refractive index of any other medium other than air, the refractive index of the other mediums are going to be greater than in air. So in this case, I'm going to assign it the value of 2. Let's say refractive index of A is 2. You understood that it's getting lifted in any other medium when you put the pencil in, when you compare it with air. The question says that NA is greater than NB, meaning refractive index of A is greater than refractive index of B. So if you say refractive index as 2 for NA, NB we can give a value of 1.5. I'm just giving values so it's easier to understand. Now we know that it is more lifted when you compare than to air, if you compare any liquid. And when you go to options, now you have option 2, it is, if it is lifted, it should go more upwards. But here it is bent downwards. So the second one will not be the answer. Same with third and fourth. It is not lifted, it's more like not lifted, like it's downwards. I don't know how to say that. So is that part okay? Like how you eliminate the option 2, 3, and 4? Okay. Then if you if you apply the same concept there, no, 4 is not lifted. Reason is, if it is lifted, now let me draw this pencil. Just think there is no water, and if you put the pencil, it is going to be straight, like it's going to be like that. If it is lifted, it's going to be more lifted like this. It's going to come like that. Okay? It's going to be higher than the straight line. You can draw a line like straight on that and check and see. Then you know whether it's lifted or not lifted. It's not convenient to do it in a device or something. If you have your tube, you can draw the line and check and see. I think the question is there. Not sure which question number though. Did you understand that part? That y fourth is not lifted? Okay. So when you compare the refractive index, so similar to this air and Na, you consider Na and Nb, we know Na has a higher refractive index than Nb. So if you compare that, we can see that Na is going to it's going to be more lifted in Na than Nb, because if air refractive index is 1, Na is 2, in a higher refractive index, it is more lifted. So if you compare Na and Nb, in Na it's going to be more lifted than in Nb. If you look at option 1 and 5, you can eliminate option 5 because it is not, in B it's not bent. It should be bent because Na is having the higher refractive index. So then answer comes as answer 1. Now did you all understand? Okay. Okay, so you all understood. Then we can move on to the next one. Okay, so this question, so people who are replying in the chat, are you all 20, what batch are you all? 25, 26 to 28? Not 25, 26, 27, 28. which page I on so that I can know 27, okay? 26, 27. So the one who is in 27, have you done this lesson before? Or any idea of this lesson? Like, do you have any idea of this lesson? Have you done it earlier? Okay, let's move on until she replies, okay? So this question, uh, okay, so you know, no idea yet. Okay, so if that's the case, this question can be a little bit difficult, and I can explain it to you. Like, I can give you a few minutes to try, but then I don't think it's possible to do it in few minutes if you have not done questions like this before. So I will directly do this question so that it's easier for you all. So in this question, they're saying a person can see the opposite side of the bottom of an empty vessel over its brim as shown in figure A. So in figure A, the light ray goes like that, and there is no water, there is nothing, and this person can see the bottom, opposite side of the bottom. And while keeping the eye in this same position, when you fill it in water, it says that the person can see the center of the bottom of this vessel. So that's going to be, he can see R, in this case R. So we know the sine R, tan R, and all of that, like Pythagoras. So basically it uses Pythagoras as well as the what do you call Snell's law, the one I was explaining the whole time. N equals sine I divided by sine R. So both of these are used here. So this is like one of a hard question. If you do similar questions to this, I think if you can do a question like this on your own, you can do optics. That's what I think. So sine I and sine R. We know sine I divided by sine R is going to give you refractive index. Now here they're asking the refractive index. So your goal is to find sine I and sine R value. So in this case, sine I, we all know this is going to be I and this is going to be R. Now there is an important line here. They are saying that you're not changing the position of the I, which means this angle, let's say this is I, then this angle is also going to be I. This angle is also going to be I, yeah. So if this angle is I, then this angle is going to be I. So they're not going to change the position. So this angle is in the B diagram is also going to be I, but this angle is going to be R because the refraction takes place and the direction of the ray also changes. Did you all understand that? Like that part about how the position of the eye and all. Okay. Then now we have to derive equations for sine I and sine R. So from this triangle here, can we get the sine value? We can't, right? Because we don't have the hypotenuse. So here's where Pythagoras comes. So you need to find this value here. So x squared actually is equal to h squared plus 2r squared. And then you can get h squared plus 4r squared and in a root. because that's going to be equal to x. So that is the value here. Now if you're going to get the sine I value, so sine I is going to be equal to opposite over hypotenuse. So that is 2r divided by root h squared plus 4r squared. So now you're done with the first part of this equation. Did you understand that part? Like how it came? Okay. Then the second part, like from the B diagram, similarly you can get uh, the angle, the sine value for sine R. So here also we don't know this angle here, I mean this side here. So y squared is equal to h squared plus r squared. In this case, it's r because it's half of the bottom. You see half of the bottom. So y is going to be equal to root h squared plus r squared. So in that case, sine value is going to be r divided by root h squared plus r squared. Okay. So these are the two values you need to substitute into the main equation. This sine I divided by sine R, which is equal to refractive index. So when you divide this, you can multiply it by the reciprocal, uh, h squared plus r squared divided by r. You can cancel the r, and it's going to be 2 root h squared plus r squared divided by root h squared plus 4r squared. And then you have gotten the equation for refractive index. So this question was repeated in another year, if I'm not mistaken, but with values. So a person who did this question and remembered the equation, they can do it much quickly by just substituting the values. Or they can also alter these letters, and they can give different versions of the same question. Did you all understand this? Okay. If you all didn't understand, anyone else who didn't understand, please reply in the chat so that I know that if you all understood or no, and if so, I can explain again if you didn't understand. Then the next concept or next part of this is going to be apparent displacement. So the thing is with this lesson, there's so much of detail that if you miss a tiny detail, you get confused. So I also used to get confused when I do this question. So I've gathered all the points that I used to miss, and then I'm like focusing on it the most. Like example, this in even in this equation, the place where the I is kept, I always confuse this. So no one told me that the denominator value is going to be the value where the I is kept. So this stuff you eventually figure out, especially when it's like nearing the exam. So yeah. Then this value here, where the I, you all can hear me, right? Can you reply in the chat? Because I think my audio went. Okay. So D equals T 1 minus 1 over N, refractive index of second medium with respect to the first medium. So this is the equation for apparent depth. So let me tell you what apparent depth is. So apparent displacement actually. Apparent displacement is the shift of the object. Hold on a second because I think the screen share stopped. Something is wrong with Zoom. Please hold on. Okay, till the Zoom loads in the other device, I'll just explain what apparent displacement is. So, apparent displacement is the shift of the image. Now, if you see the image there, the object is at the bottom, and if you know the coin before, it lifted a certain distance, right? When you pour the water into that particular bowl, the coin suddenly appeared. So that lift is called apparent displacement. So that lift, the equation to find that apparent displacement is the one that's shown on that's there. D equals T 1 minus 1 over N, which is refractive index of second medium with respect to first medium. I think the Zoom is not working, the laptop, so I'll try sharing the screen. Okay, someone is asking me about if the remaining lessons will be covered, like optical instruments. I think yes, it depends, but I'm not sure. I don't think it's like in recent weeks. So this one, I should ask the admin and let you know. But I think yes, we can make it happen. Inshallah. I'm still waiting till this screen gets loaded. Give me 2 minutes. I'm so sorry. I just switched the device and come. I'll bring the other laptop and come, please. It will be done, I think, after 26 A levels because it's like a webinar series that's going on. So, yeah. Give me a few minutes until I set this thing up. Can you all see the screen? Let me know if you all can see the screen. Okay. I'm so sorry. Zoom suddenly stopped responding to me. Okay. I'll continue with the lesson. So regarding this apparent displacement, so you need, I hope you all understood what apparent displacement is. It's the shift of the image. It's the shift of the image, like from the position of the object. So this part right here, that is the apparent displacement. So d equals t, the thickness or the length of the medium, into 1 minus 1 over n. So one important thing again is where the eye is kept. The location where the eye is kept is very important, because if that goes wrong, your entire simplification, even if you do the simplification right, even that is wrong, because the main theory is wrong. So this is how you find D using this equation. And about lateral shift, you can write this equation down in the tube. There's a box there. And about lateral shift, this topic, I was taught this topic by one of my sirs, and he taught me this, but I haven't seen any question from this. So I'm just, he taught the derivation as well. So, but that is complicated. If you want to know the derivation, you can drop me a message. I can send it to you, but it's not necessary. So the main thing is the equation. So lateral shift is the shift, or it's like how, by how much the ray has moved in a perpendicular, in a horizontal, in a perpendicular direction. So initial ray is supposed to go like this, like that. That's how the initial ray is supposed to go, but it has actually shifted here. So you're going to find this distance. So the perpendicular distance to the original pathway. So that is what you're going to find. So that value is x. So x is equal to t, the thickness, sine I minus r. So sine I minus r is this angle here. I minus r is the angle here. So that is the difference in the angle. So sine I minus sine r divided by cos r, the value of r. So that is what you should know in this. If you know the label the parts and stuff, you can find it. But I haven't seen a question on lateral shift in any of the past papers, and I don't think it's there in the resource book as well. So I will just thought it. I'm just teaching you in case it shows up somewhere, and then you can say that you have learned it before. Then moving on. So again, this part, it comes under the MCQ points in the tube. So did you all understand the lateral shift? And it's just the equation that you all should know. You can write that equation down in the tube as well. So this is about MCQ points. So these points are there. I've given it in the tube. I think this image is there in the tube. One point is when the light ray is traveling through the each medium. Here, if you look at this, the medium it starts in is A, and medium it comes out in is A. It passes through several mediums. It can pass through, let's say, B, C, D, all of these mediums, and it ends up in A. One thing you can know is these rays, although the position is different, these rays are always parallel to each other. So when it enters the medium again, the ray is going to be parallel to each other. So that is the first point. The second point is that you know apparent depth and refractive index. So we know real depth, let's take it as R, and apparent depth as A, is equal to refractive index. We all know that. So if refractive index increases, apparent depth decreases. So this is inversely proportional to each other. So when it increases, apparent depth decreases. So you can use this concept when you're comparing two liquids. So if you let's say water and let's say some sort of liquid, let's say honey or something. So when you compare both of this, you can say the medium which has like higher refractive index, the apparent depth is also going to be small. That means the apparent shift is going to be higher. Did you understand that? So let's say this is apparent shift, apparent shift, and then let's say image is here. This is the medium. This is apparent depth, and this is real depth. So when the refractive index increases, the apparent depth decreases. So this apparent depth, when it decreases, it moves more towards the surface, which means this apparent shift value is going to increase. So that is one way you can use. I haven't seen a question where they compared different liquids before, so this can also come as an MCQ maybe for your exam probably. And then the next part is when the object is placed in the same medium as the eye. So the eye is in air here in this image. Eye is in air and the object is also in air. If and then you apply your equation for what do you call apparent shift, apparent displacement or apparent shift. D equals T I minus I 1 minus 1 over n. If you apply this equation, you get a value for D. This value is the same value that you get if you place the object at the bottom of the medium you're seeing it through. So this depth here, this shift here, apparent shift here, when you look through the medium while the object is in the same medium as the eye, or if you are looking through a medium and the object is at the bottom of the medium that you are looking through, this apparent shift is going to be the same. This is another point, MCQ point. So you can write that also down. Did you all understand that? Like this slide? If so, we can move on to the next part. Okay. So these are all, it can be like very tiny points, but at some point it can some like suddenly appear in the paper, so that I'm telling you all now, so you all won't be shocked when it appears. Because there have been years that suddenly certain concept which has never been questioned, suddenly when it comes, we start panicking. Okay, so this one, usually when you explain this question, usually people explain only one side of this question, which is the situation one. Now I'll take this first image as situation one and this image as situation two. So in situation one, the object or not object, the observer is in a rarer medium, example air, and the object is in a denser medium like water. Or in this case, this diver in air, this diver who is like going to jump in air, sees this particular diver who is underwater, observes this particular diver underwater. So this person, the person in the rare medium who is in air, sees this diver as he's lifted above. So the apparent it's shift, his image is shifted, and he sees more that this person is more towards the surface. So that happens in situation one. In this case, the apparent depth So apparent depth is this value here. I'll name it as AP. Is greater than is less than real depth. So real depth, it's uh, it's apparent depth is less than real depth. Then we also know that the object is being lifted or raised. So the apparent shift will increase, like it appears more close to the surface. Now, if I am going to explain the situation 2, here the observer is in the denser medium. So in this case, uh, let's say the observer is the diver who is underwater. This particular diver observed this person who is about to jump in. So he observed that person, and the image of this person appears much more higher. So it is further away than he actually is. So this diver sees this person further away. So that happens when the observer is in the denser medium and observes an object in the rarer medium. So if you look at this, the apparent depth is this value here, apparent depth, and this value is going to be the real depth. So in this case, the apparent depth is greater or much larger than the real depth. So that is the difference between both of these situations. Usually people don't teach the second situation. I don't know why, but I feel like you should know that, because suddenly, like, I don't know, it's like it's not complete. The theory is not complete if you don't know that. So did you all understand this, both the situation 1 and situation 2? And how the object is far away, moving further away, and how in situation 1 the object is raised. If you all did understand, send a message. If you all didn't understand, also send a message. Okay. Then I'll move on to the next part. So this is a question based on the earlier, what do you call, earlier theory. So situation 1, situation 2. So I took this from a book. So if you all want, you all can try it, or should I wait? Should I do it for you all? How do you prefer it? Should I do it, or do you all want time to do it? Okay, then I'll do it, and then you all can follow along. Okay. So in this case, they're asking the apparent depth of how each of these objects are perceived by the observer. So in this case, there is a crane and there is a fish, and the crane observes the fish. So the one that's marked here is the real depth, and we are going to find the apparent depth. So let's take crane. So this is situation 1. The crane is observing the fish. So crane is in the rarer medium and the fish is in the denser medium. So crane observing the fish. Real depth divided by apparent depth is going to be equal to refractive index. Now we know absolute refractive index of water is 4/3. This is the refractive index of water with respect to vacuum. So it's going to be water and air. So this is the refractive index that is used here. So in situation 1, the real depth is 6 meters. Apparent depth you're going to find, let's take it as x, and that is going to be equal to 4 That's going to be equal to 4 over 3. Yeah. Hold on. Wait, I made a mistake. Now, uh, yeah. Okay, so y'all also can make mistakes like this. So they are asking how the crane sees the fish. But I took this as the depth. I didn't take 8, I took it as 6. So we are going to see how the fish, what the apparent depth of the fish is. So we are going to find this value. So in this case, you have to use 8. So if you all are careless like me, you can make mistakes like that as well. So x is equal to 6 in this case. In this case, the apparent depth at which the crane sees the fish is going to be 6 meters. Now, if you take situation 2, which is the other way around, where the fish sees the crane. When the fish sees the crane, there's a small change that you have to do in your equation. Now, if the fish sees the crane, we know the real depth of by which the crane is observed by the fish. It's going to be 6 meters. So real depth, apparent depth, we'll take it as y, is going to be equal to refractive index. So now refractive index we know it's going to be medium 2 with respect to medium 1. So this refractive index is NWA. But in this case, we know that the eye or the observer is the fish and the fish is in the denser medium. Observer is in the denser medium means this A should be replaced with W. So it should be N A with respect to W. So refractive index of A with respect to W. So if that's the case, you're going to do a reciprocal. So 4 over 3 is going to be taken as 3 over 4. So then you can get this, you can substitute and then you can get the value as 8 meters. Y equals 8 meters. Did you understand this part where you're going to do the reciprocal and why you did the reciprocal? If you all understood, or let me know. Just let me know. Okay. Okay, someone asked me to explain again. I'll explain it again then. So I hope you understood the situation 1. So situation 1, we have a refractive index of water, and that refractive index, that means this one right here, 4 over 3, is refractive index of water with respect to air. So we know N equals C over Cm, the medium. So here medium is water. So NW is C over Cw. So that is what comes here. So it is compared with air. And I always said that, I said this before, that this first medium that's marked here, A, this one is going to be the place where the eye is located. Eye should be located in the medium that's given, that I have marked here. So when you consider the fish observing the crane in the air, so the fish here is in the denser medium, which is water. So your equation or your refractive index should be like this, such that water is the place where the eye is located, where the observer is located. So in order to do that, in order to get that, you can reciprocal this as 3 over 4 and you can get the value for refractive index of air with respect to water, because the location of the eye is important. So did you understand now? If you still didn't understand, please let me know. I can tell again. Did you understand why we reciprocate? Okay, I'll tell it again then. So, did you understand that 4 over 3 in this, the one that they have given, absolute refractive index of water is going to be uh, n. Did you understand that this is going to be the refractive index 4 over 3, where water is, refractive index of water with respect to air is 4 over 3. Is that okay, that part? Okay. So you understood that refractive index of water with respect to air is 4 over 3. And I also said that you have to look at this first letter, and this letter is the place where the eye should always be located. Eye in the sense the observer. Here, the first situation, the crane was present in air. So since crane is present in air, crane is the observer, we can use this equation, this refractive index directly. But now here the fish becomes the observer. Since the fish becomes the observer, you have to shift your refractive index to look like this. Did you get that? Because you want this to be where the location of the eye is going to be. Did you get that part? Okay. So in order to make this one from this one, you have to reciprocal this. Basically, you should switch the position of numerator and denominator. So 4 over 3 is in the first situation, but in this situation, it's going to be 3 over 4. Did you understand that? Okay. So because of that, now if this fish is observing the crane, so this is the real depth of the crane, 6 centimeters. Apparent depth is what you're going to find. And the refractive index, now in this case, we are taking as 3 over 4. And when you simplify, you get y is equal to 8 meters. Now, okay? Now, did you understand? Okay. Then we can move on to the next. This I did this part so that I can show you that you can apply it in both ways. Because usually we don't learn it. Like most of the people don't teach it. Which I have no explanation as to why they don't teach it. I know it's extra information, but it's nice if you know the whole idea, especially like if you're just starting to learn this. Okay, moving on. These are the remaining MCQ points. So there's a lot regarding apparent depth and all of that. So this concept, it may seem small, like everyone teaches a very little, but if there are other points. So if you use this apparent shift equation now, so this is the equation for apparent shift, D equals T 1 minus 1 over N. If you apply this equation to situation 2, as I mentioned, when the observer is in the denser medium, so observer is in water and it's observing an object, let's say O in air. In this case, if you apply this equation, you're going to get a negative value for D. So that means the apparent shift is going to be negative. It just denotes that the image is moving further away. Now, if I go back to the previous slide, I can show you. Uh, over here, how this has moved further away than the object. So this diverity. So that part. Then, so if you're applying that scenario, you will get a negative answer. So it can come, I think it would be a very nice question for essay because most of you all don't know. And when you suddenly get a negative value, some of you all will get stuck. So yeah, to get a negative value, don't get scared. Then the other concept is to find the total apparent shift by how much the total image has shifted when you look through multiple mediums. So here medium, the second medium, third medium, and so on. When you look at this, here what you should do is you need to add the apparent shift individually. D equals, now here let's take for the first medium. So let's take as D2 because this T is also 2, so you won't confuse. T2, 1 minus 1 over N2 with respect to N1 because this is the medium where the I is kept, plus D3, uh, D3. So D3 is T3, 1 minus 1 over N3 and with respect to 1 because that's the medium where I is kept. Similarly, you add for the next medium also. So this is going to be the total apparent shift. So always remember this where the I is kept. It's always important. If you switch that, then your whole answer will go wrong. So there has been MCQs on this point before. Okay, then the next part, we all know real depth divided by apparent depth is equal to refractive index and all of that. We know when thickness increases, the real depth increases. So thickness increasing means the depth of the medium is increasing. So real depth increases. If real depth increases, the apparent depth decreases because they are inversely proportional. No, apparent depth increases uh, because they are directly proportional. So when the thickness increases, apparent depth also increases. Reason is directly proportional is when you take R equals N, if you take this to the other side, and N is a constant, R is directly proportional to A. So you can get it from that. So when thickness of a medium, particular medium decreases, let's say this T3, it becomes thinner and thinner and thinner. At one point, the apparent depth will also decreases. Apparent depth will keep on decreasing when the thickness decreases. At one point, the apparent depth will be equal to the real depth because it will coincide with the object and there won't be a medium anymore. So that is what meant by coincide with the object because the medium is over. So when the depth is greater, the apparent shift is greater. You can understand this last point from this equation that's on the top. So when the depth is greater, that is thickness increases, the apparent shift also increases. So these are points based on the direct proportionality, inversely proportional, all those stuff. So based on these points, those based on these equations, these points, I have taken it as that. So you can remember it as point because many people don't notice uh, these proportionality things. So in some questions, it can come as useful. So these points, I'll send the slide later. You can write it down in the cute if you didn't write it down. So this question, I think you all can try this. So can you all try this and let me know your answer? Like, I give you 2 or 3 minutes. You can try it and let me know. So if you all did the question, please send the answer in the chat. Or if you all are still trying, please let me know if you're trying the question. Maybe like a thumbs up or something, a reaction. Okay, then I'll continue with this. So, or if you all are trying it, please let me know, because if not, I'll move on. Okay. So if you consider this question, it's actually not hard. So it's just you have to think a bit more. So here they're saying there is a glass cube with side length 24 centimeters. Okay. And then there is a bubble or air bubble, I think. Air bubble in here. And the refractive index of this glass is 1.5. You can write it as 3/2 to make your calculations easier. And then they have yeah, and then they have said that when you view it from one side, the bubble appears to be 12 centimeters. So here the word appears to be, it's like what you can see. So what you can see is the apparent depth. So you can see the apparent depth. You can see the image of the bubble. So that image is going to be 12 centimeters. Now they're asking, how far will the air bubble appear from the other side? So when it appears from the other side, it's going to be the apparent depth of the bubble when you view from the other side. So first we must find what is the actual location of the bubble from this side. Let's say X. So we know real depth is what you're going to find. That's X. Apparent depth they have given as 12 centimeters. That is going to be equal to 3/2. So when you calculate this, we can cut 6, 6, 12, 18. 18 centimeters is X. So if X is 18, 24 minus 18 is going to give the real depth of this side of from this side of the cube. That's okay? Did you all understand that part? How it's how you get that? Okay. So you're getting the value as 18. So 24 minus 18 will give you the real depth from the other side. That is going to be 6. So 6 is the real depth when you view from the other side. So they are asking, how far will the air bubble appear from this side, from the side that you are viewing? So it appearing is the apparent depth again. So real depth divided by apparent depth is going to be equal to refractive index. So real depth in this case is 6. Apparent depth is what you're going to find, and that is equal to 3/2, the refractive index. So 362 y is going to be equal to 4 centimeters. So that is your answer. Did you all understand this one? Okay. So I'm planning on ending the session now. How many of you all want to continue more? If you all want me to continue more, you can let me know and I can do so. If you all don't want to continue more, you can say that as well. So you can stop the meeting here because the time's up and I got delayed in the beginning for like half an hour due to technical issues. So sorry about that as well. If you all want me to end the meeting now, you can let me know. Or if you all want some more, you can let me know about that as well. Because the next part is about critical angle and it's a totally new, different part. Okay, since none of y'all are replying, I assume that y'all are tired of this and y'all don't want me to want to say it to me. So we can end the meeting here. If y'all have any, okay, someone wants the water droplet part. So others, if y'all don't want to listen, you can leave. I'll do the water droplet part for uh the one who wants it. So water droplet part, it's not that hard. It's like it's just so usually these questions in about water droplet, it has appeared in much older papers actually, but it has come in essays as well. Okay, someone wants prisms also. Okay, whoever is tired can leave the meeting, but I keep continuing for the people who want. Because the time's also up. So let me move on. Okay, so water droplet. So other people who are planning on staying, I think someone named HO. So if you're planning on staying, have you done this lesson before? Like critical angle, do you know about critical angle, total internal reflection and stuff like that? At least a little bit, like critical angle. So then you can understand this much better. Okay. So if you know this, we can directly do this water droplet part. So regarding water droplet, so usually we know there's something called total internal reflection, which happens when the angle of incidence is greater than the critical angle. So if you don't know about critical angle, so critical angle is when a ray enters from a denser medium. When it enters a rarer medium, the angle at which the incident angle at which the refracted angle moves along the boundary is critical angle. So when the incident angle is greater than critical angle, when you increase it more, it starts moving into uh, the same medium. So that is total internal reflection. So in this case, in a water droplet, this total internal reflection concept, it doesn't take place. There's something called partial reflection that takes place. So that happens inside a water droplet. So if you take a water droplet, what you should focus on in first is the normal, the normal line. So we usually draw normal line perpendicular to a medium, but a water droplet is more circular. So the normal, it always passes through the center, the center point of the water droplet. So this is the normal for this point, this is the normal for this point. Okay. So when you take, let's say, incident angle here is I, and it's coming from air. Air is rarer medium, and this is water. It is a denser medium. And when this is incident on the water droplet, when the incident ray is on the water droplet at the angle of incidence, since water is more denser, the light ray it moves towards the normal, more towards the normal. It is supposed to go this way, the ray is supposed to go this way, but it actually has come this way towards the normal. And the normal is always to the center in a sphere. That is very important. If not, you will go wrong with the questions. And we also know that if this is a particular, now let's say the ray got refracted and it's coming to this particular point called point B. So at this point, we know the refracted angle R, yeah, and then this is the radius of this circle, and the other radius, this point that connects the center with B is this radius. This and this is equal, which means it's like opposite angles of equal sides are equal, the O-level concept there. So this R is also equal to this R there. So this angle is equal to this. Similarly, when this is reflected, or when it is reflected back, this R here, so this will be equal to this, and then that same R is also here because this side is equal to this. Basically, because the radiuses are equal, the R is equal at all these points. So since it is incident on the same surface, again it is air and water again, when it is coming out of the water droplet, the angle it forms is I, the same angle as it is incident. So that is basically this diagram. And so here at this point B, it has a total internal reflection. Then there is another thing called deviation. So deviation is the how the pathway of light has changed from its original pathway, by how much the value, you can find the value. So let's say this one, the incident ray it's like this, and the ray is supposed to go like this, but it actually has gone like this. So this is the deviation, the change. So that deviation you can find. So if this is vertically opposite angles, right? So this is I. So I minus R is going to be equal to the deviation at A. Did you all understand that part? Okay. Then to find the deviation at point B. So in B, the ray comes like that, and it is supposed to go like this, but it actually goes like this. So how you find that is, we know this is 180 angles in a straight line. Again, O-level thing. 180 minus 2R. If you subtract these 2R, you get the deviated angle, this part here. It is equal to D, deviation at B. Similarly, if you take C, it is supposed to go like this. So the ray is supposed to go like this, but it actually moves this way. So there also DC is equal to deviation at C is equal to I minus R. So the total deviation in a water droplet, if you add dA plus dB plus dB plus dC, you're going to get the total deviation. So total deviation in this case is going to be 180 plus 2I minus 4R. So this is the value for deviation, the equation for deviation. So this is the main concept of water droplets. So did you all understand this? Okay. Then moving on to the next slide. So it is a little bit more on water droplets. So this, it's not that hard. It's just a bunch of other concepts together. If you integrate, you can get the concept of the water droplet. Okay. So the reason I taught you about total internal reflection is to show that water in a water droplet, total internal reflection can never take place. So we know total internal reflection is when the angle of incidence is greater than the critical angle. That is when it moves 90 degrees or along the boundary. So let's say it is incident with an angle 90 degrees as shown here. So when it moves inside, it moves with a critical angle. You all understood this part? If it is incident at 90 degrees, the refracted angle is going to be it's going to be critical angle. Did you all get that? Okay. Then, and we know this is going to be C here again, and then here also it's going to be C, and then it comes in a 90. So in this place, total internal reflection can never take place. I'm going to explain that part. So we know I should be, incident angle should be greater than critical angle. So, but in this case, the incident angle at this point, let's say B, is equal to critical angle. It's not greater. Since it's equal to critical angle, the reflection that takes place here, it's not called as total internal reflection. It is instead called as partial reflection or critical reflection. So that is the concept here. So reason as to why total internal reflection can never take place in a water droplet. Did you all understand that? Okay. So that is regarding water droplet. So these are the two main concepts regarding that. The other part is the dispersion of the light rays when it is in a water droplet. So let's say, okay, so there is a question here. Would you like to try it or you want me to explain it or something, anything? Because in this question, although there was deviation, there is one extra point that you should be careful about. So do you all want to try it? Let me know. If not, I can do it for you all so that you all understand it. Whenever I ask about a question, all of you all are silent. Okay, I'll just do the question then. Looks like none of you all want to do it. Okay. When you consider this question, they're saying this this what do you call, it's a glass sphere, and it incident ray of 60 degrees at the incident angle 60 degrees. You have to draw the normal to the center. If not, your answer will go wrong. 60 degrees. So the extra, and then they are saying n is equal to root 3 refractive index. They are asking the total angle of deviation. So in this question, there's one important concept. So that I will eventually, while doing the question, I'll tell you. If not, you all will be like, uh, how can that happen? Okay, so now we know that incident sine I divided by sine R is going to give you refractive index. Now we know the sine I value. If you find sine R value, you can find the R value here. Okay, you can find the R value there. So sine I is sine 60. Sine 60, value is root 3 over 2. Sine I, the value is root 3 over 2. Divided by sine R is equal to root 3. So sine R, the value of sine R is going to be, you're going to get the value as half. Then R in this case is going to be 30 degrees because sine inverse of half is going to be 30 degrees. So R is 30 degrees. So now we know that. Now one thing that most of you all will do, you all will name this as R, and then since the theory is saying that since R is 30, when because total internal reflection cannot take place, this is also R, and this angle here also is R. So if you take like that, you're totally wrong, because there's one other concept that comes in, and that is critical angle. So the critical angle of glass is 42, approximately 42. Since I didn't explain this in order, so this part will suddenly come in. So there's the order where I arranged the presentation where this part is already taught before. So critical angle for glass is 42 degrees. So we know if the incident angle is greater than critical angle, total internal reflection can take place. But if the incident angle is less than the critical angle, then refraction will take place. Did you all understand that part? Now let's say this is 60 and then it is incident at this point. We know that now R is equal to 30 degrees. So R is less than critical angle. Since R is less than critical angle, refraction takes place. Did you all understand that? That refraction takes place instead of reflection. Okay. Since refraction takes place, uh, we know that since again here R value is here, same R value, we know that it will move away from the normal at an angle 60 degrees. Incident the same values apply again. Then if you find the deviation, so it is supposed to go like this, ray is supposed to go like that, but it actually has gone this way by 30 degrees, and even at this point, it is supposed to go straight, but it has gone down 30 degrees in the same direction. So that is going to be 30 plus 30, which is 60 degrees, which is the angle of deviation. So did you understand that part? So here the thing is 42 degrees. You have to keep in mind, because in some questions they give, some questions they don't give the critical angle. Did you all understand? Okay. Then I'll move on to the next part of this water droplet. The next part is not that hard. It's about the dispersion of. You all know about white light, right? How it splits into 7 different colors when it refracts through a prism. So same concept applies to a water droplet when it gets refracted. When it gets refracted to a water droplet. So okay, you can look at this. There's a YouTube short here. So there's a particular rainbow forming, and where basically these water droplets in air, they only form the rainbows that you actually see. So there is multiple water droplets, and when the sunlight hits this particular water droplet at this point, the white light, it splits into 7 different colors. One point that you should know, violet, the color violet has the highest deviation, meaning it moves further away than any other ray to like away from any other ray. So let's say original path is supposed to be like this, but red is having this line here and violet is having a line here. So more than the initial or original pathway, some rays, example the violet ray, moves further away, so it has the highest deviation, and then it gets refracted the same phenomena and comes out as a rainbow color. So many of these water droplets together, it will form the rainbows that you actually see. So that is regarding this splitting of the light in rainbows. So I think there are essay questions in this. You can try some essay questions on this water droplet concepts. MCQs, there are very few, but essay questions, there's a lot. So uh, this question, it's easy, but there's a small twist. Okay, so do you all want to try it or no? Again, no. You all don't want to try it. Shall I do it for you all? Just let me know. I think it's useless asking because you all don't even reply when I ask about a question. Can still do the question. If not, it's waste of time for you all. Okay, so the twist in this is earlier we were speaking about a glass sphere in air or a water droplet in air. Usually that was what we were doing so far. But in this is a air bubble in water. So it's the opposite. So air bubble in water, which means from a denser medium, the rays are going into a rarer medium. So in this case, we have one light ray that hits this part, and then we have a normal, we can draw the normal, and then it meets at the center. Let's say the center is not in the center, but it's in the center. Okay. So when a light ray enters from a denser medium into a rarer medium, we know that the light ray moves away from the normal. If the light ray moves away from the normal, you're going to get a ray like that, right? So same with the bottom ray as well. So you draw the normal and the light ray moves away from the normal. And again, at this point, you draw the normal again to the center. And we know from a rarer medium, if it moves to a denser medium, it moves towards the normal. From a rarer medium, if it moves to a denser medium, it moves towards the normal. So your ray diagram is going to look like this. So here answer is answer number 3. Did you all understand that? Okay. So basically, physics is more about English. So if you don't read the question properly, you're done. It's like you should know how to analyze what they are saying and rearrange it in a way that you're going to understand. So someone wanted prisms as well. So I'll do prisms also if you want. So prisms, this is the theory of prisms, and the theory is not that hard. Then there are practical questions that you get in prisms. So I think the past 3 years they've been getting optics practical. So I think this year optics practicals might be highly unlikely, but if the government, if they want to do some play with you all, they will put optics again. So it happened with the 25 paper where we all, most of us, expected waves and then they put optics. So it can be the same for you all as well. And one such practical is practical 16, which has come only once, I think only twice, 2018 and 2021. So it can repeat if an optics practical is coming, but I think it will probably come for a 28 paper, 27 paper, which is, yeah. So regarding the practicals I just mentioned. And moving on to the lesson about prisms. So I'm just going to explain you. Um if you all do you want me to explain prisms as well, or is that enough? Just let me know because I think it's going to take a little more time. It's going to be 12 also. If you all want to sleep, or yeah, who are not studying, who are done studying for the day, if you all want to sleep, let me know. Or if you all want to continue, that also is fine because it's going to take a while. You want me to go over the concepts of prisms? So you know the equations that are used in this lesson in prisms? Do you know the deviation equations and all those? Okay. So the person with HO, do you know about deviation and all these equations that's there? The equation that's there on the screen, do you know about that? How it came and all? Okay, so one person knows, one person doesn't know. So I'll teach it so that it's convenient for everyone. So regarding prisms, so first thing I'll do is I'll explain the diagram. We know incident ray, refracted ray, and the one that comes on the other side of the prism is called emergent ray. So we have I1 as the incident angle, I2 as the emergent angle, the angle that comes out, and R1 and R2 as refracted angle as well as the incident angle in the second surface. So these are the parts that's named. So the original pathway of light is this pathway. And then in this also, similar to the water droplet concept, there is a deviation. So deviation is by how much or the degree of angle, the angle by which it has moved away from its original pathway. So if you take this ray, incident ray, it's supposed to go along that line here, and then, but it actually has gone this way. So this angle here is the deviation at the first surface. I'll name it as D1. Okay, deviation at the first surface, D1. If you take the second surface, this ray is supposed to go like this, but it has actually gone this way. So, yeah, so it has actually gone this way. So that is D2. The deviation is D2. The sum of this deviation, you can show the sum of deviation of both surface as the D that is mentioned in the diagram. How that comes is, this is the original pathway of light. It's supposed to go like that. But in the end, it actually goes this way. So if you extend this line, it extended the wrong way. If you extend that line, it goes and meets at that point. So the angle between this is deviation. So that's called the deviation, total deviation. How you find this is you can add the deviation at this surface and the deviation at this surface. So deviation at this surface is this angle right here. This angle right here, that is I1, uh, I1 minus R1. So the deviation at this surface is going to be Now, if you draw the line like this, so this is going to be R2. If you find, I think the diagram is not clear. So at this surface, it is supposed to go like this, but it actually has gone this way, which means the deviation is this particular part here. So now if you draw, vertically opposite angles, so this is going to be I2, and if you draw this line here, it's going to be R2. The angle, so this is going to be R2. So this angle here is the deviated angle. You can get it as I1, sorry, I2 minus R2. So if you add the deviation of both this, you get this equation right here. You get I1 plus I2 minus R1 plus R2. So you all understood that, I guess. Then, if you understood, let me know. HO person. Okay. Then, how this A comes into this equation, I'm going to teach you that next. So now if you isolate this part of the diagram, this particular part, you can see that this is the normal, which means this angle right here is going to be a 90-degree angle. Similarly, this angle here is going to be a 90-degree angle. Then if you want to find the angle here, you can take it as 90 minus R1. This angle here, 90 minus R2. Then we know angles in a triangle A plus 90 minus R1, 90 minus R2 is going to be equal to 180. And in that case, you get R1 plus R2 is equal to A, because this 90, and this 180, it cancels out. You get R1 plus R2 is equal to A. And that is how this A came into this equation. So that is basically about the equations, and I hope you understood. Let me know if you understood that also. Okay. Then I'm going to tell you about the next part. So, wait. So this is, I'm going to talk about the direction in which, oh no, it's skipped an extra, this one. Okay, I'm going to tell you about the direction in which the ray moves when you change the value of the angles. So this concept is used when you're doing the practical to find the value of deviation and the value of the A. So here I forgot to say it means prism angle, the angle of prism. So if you didn't know, that was the angle of the prism angle. I've been saying A the whole time, I didn't define it. Okay. So the concept, what happens is, first, when you increase the value of I1, we keep increasing the value of I1. This angle increases, it keeps on increasing. Let's say it was on the normal, and then you're like increasing the value of I1. When you increase the value of I1, the deviation value, this deviation value, let's say you increase the value of I1, even the, what do you call, this angle, the deviation angle, it decreases, as well as I2 also decreases. So when you increase I1, slowly when you increase I1, this refracted ray, this R1 over here will also increase. So it will go like that. When it goes like that, we know that even the refracted ray, it's going to be like so much higher, like so much higher, the location. Because of that, this deviation, this angle will also decrease. This deviation angle will decrease and I2 is also decreasing. So here I1, when it increases, D value decreases, deviation decreases because I'll tell it again, because initially it's supposed to move like this, but it moves like this. But when you increase the value like this, we know R1 value also increases, so the ray will move somewhere like that. Ray will move this way. And then at this point, you can see I2 will also like it will refract and I2 angle will also decrease. So that is the main concept behind this. So at a certain point, when you keep on increasing I1 value, at a particular point, this D value becomes gets a minimum value. D becomes a minimum value, and like further, like more than that, you can't decrease D. So let's say D is like this. This is D. Let's say after all this process, at one point D reaches its smallest value. It's like it's not going to be 1 or something, it's going to be like 15. You can't further, when you increase I, D won't increase, like it won't decrease more than that. Because of, and then D reaches a minimum value. So that minimum value is called the minimum deviation. So D means deviation. So minimum value it reaches is called deviation. So when at that point, D becomes a certain value. Let's say I was like this is I at that point. Now you increase I further. Keep on increasing I, but D it stops decreasing. It doesn't decrease anymore. The D minimum deviation value doesn't decrease anymore. Instead, this ray it moves in the opposite direction. It starts moving, and the D value starts to increase. So D value increases when it moves further and it changes the direction and D value increases. At the same time, I2 value also increase. So it reaches a minimum deviation and the ray changes its direction, and then D value increases and I2 value increase. So did you understand that part? Okay. So that is you can use this concept in there is a practical where you use this concept. So you look it through a spectrometer if you haven't done that before. uh, when you come across that, it's a device where you can see the movement of rays, and at one point the ray moves in a opposite direction. So that is about this, like what happens. So what actually happens, you can write it in a graph. Now I said the value, so this is deviation, this axis is deviation, this axis denotes y. So you slowly increase I, the value of incident I1, and at the same time the value of D decreases, and at one point it reaches a minimum value that is called minimum deviation. And then when you increase I further, the value increases, D value increases. So that is what is explained in the graph. So this graph, this is like a standard graph. The shape won't change. Someone has asked how the ray changes the direction. So it's like this. Wait, let me go back. Regarding the direction, let's say now you have increased the I value to this point. Let's say here. Have increased the I value to this point. At that point, the D value is like somewhere something like this. More than this, the minimum, it cannot increase, it cannot decrease more than this. So when you increase the I value, this ray, that means this emergent ray. So earlier, when the ray is struck, it comes like I comes here, I2 comes here. Now when you increase I1 further, it changes direction in the sense this ray, first it was moving like this, it starts moving downwards. Like this ray, it moves downwards. Do you understand that? And that is why D starts increasing. Since the ray changes its direction after reaching a minimum value, uh, the value of D also changes. Did you understand that now? Or do you want me to tell it again? Okay, it wasn't clear. I'll tell it again. So I said you increase the value of I1, and at that time the value of D decreases. Did you understand that part? That the value of D can decrease when you increase I? Okay. So, and then you keep on increasing I. Now, if you take a look at the graph, we'll show the graph. You increase the value of I. This is the axis of I. You increase the value of I, and it reaches a particular point where when D will start decreasing, and at one point the D will obtain its lowest value. That is called minimum deviation. You understood that? Yes. Okay. Then when you further increase the value of I, the value of D will start to increase. So according to this graph, it starts to increase. So reason it starts to increase is because, oh no. Um, so the reason it starts to increase is because the direction in which the light ray moves starts to change. I'll show it to you. Wait. Mm, okay. So let's say now D has reached its minimum value. Let's say this is the light ray, incident ray, refracted ray, and then you draw the normal, and I is like this. Now when you D reaches a minimum value, and then if you increase I further, I1 further, this D here, this ray here is going to move this way. First, initially it moved this way, and now it's starting to move this way. So that happens inside a prism. You can't see this actually. It's like because it's a light ray, you can only, I think with using laser you might be able to visualize this. I didn't even think of including a image. I can maybe search one and send it to you. So this ray, it increases. This ray starts to move in this direction. When it starts to move in this direction, the D value over here will increase because the ray will start to come here. Then this D value increases. Now, did you understand that part? Okay. So that is about this. Then we can move on to the next part. So, did you understand this graph? Okay, that is also okay. Then one thing you should know is at this graph, although I'll tell that part later. So at minimum deviation, there is two things you need to know. I1 is equal to I2 and R1 is equal to R2. That is, the incident angle is equal to the emergent angle. So at minimum deviation, this is the point, this part here, you see from both sides it's the same value. So I1 is equal to I2. And at the same time, if I1 is equal to I2, since this is a prism and there is two mediums, air and glass. So if the incident angle is same, refractive index is the same, refracted angle will also be the same. So R1 is equal to R2. Did you understand that part? Okay. So that is about minimum deviation. There is one other point that is there that I forgot to mention. So when for a particular value of deviation, now I'm not talking about minimum deviation, I'm talking about any other value for deviation. So let's say value here, let's say it's 50 or something. So this point here, not here, let's say this point is 50, and for this point you have one value for I, and this is the other value for I. You have two values of incident angle for that particular deviation. The reason you have two angles for that deviation is when you draw, like let me draw a prism, and then you have incident angle, incident ray, refracted ray, and then the emergent ray. So incident angle I, let's say it has this value, then the emergent angle I2 will have this value. So let's say you reverse this ray, and you reverse the refracted ray, the emergent ray, and then the light ray actually moves in this direction. Then your incident angle is going to have this value here, and your emergent angle is going to have this value here. So this is again the reversibility of light concept. So let's say this value is 20 and this value is 50. Incident angle initially it's 20, then this emergent angle is 50 at one particular deviation value. Then when you reverse the light ray, then the incident angle is going to be 50 and the emergent angle is going to be 20. So at this case also the D value is going to be the same. Did you all understand that? There are two values of incident angle for a particular deviation value. If you all understood that, let me know. You all didn't understand, I can explain again. Okay. 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 Then I can move on about more about minimum deviation. So about minimum deviation, as I said, I1 is equal to I2 and R1 is equal to R2. Now we have the initial equations, right? R1 plus R2 is equal to A, and I1 plus I2, and then deviation is equal to I1 plus I2 minus A. So initially, I write it again. R1 plus R2 is equal to A, and you have D is equal to I1 plus I2 minus A. So since R1 and R2 is equal, you can get R equals A over 2, and you can subtract this. Since I1 and I2 is equal, you can get it as 2I, and when you substitute you can get I equals A plus D divided by 2. So you take this minus A to the other side, it will be plus A plus D, and it will be 2I. When you take the 2 to the other side, it will divide, and then it will be I is equal to A plus D divided by 2. And then we know n equals sine I divided by uh, sine I divided by sine R. So refractive index. Again, back to that Snell's law equation. So you can use this value at minimum deviation. So keep in mind at minimum deviation. No other uh, like not you can't use it in any other situation, not any other deviation. Only minimum deviation. When you apply this sine I divided by sine R, you can use instead of R, you can use A over 2 sine A divided by 2 over here. And instead of sine I, you can put sine A plus D divided by 2. And then this is like the numerator. This part is the numerator. And this part is the denominator. You understood how that came? Did you guys understand that part? Like how the equation for minimum deviation, the refractive angle, refractive index at minimum deviation is derived. If you understood, let me know. If you didn't understand also, I can tell it to you again if you don't mind. So I hope you guys understood. I'm going to move on to the next part. Okay, so we got two questions. So you can try this. It's actually easy, not that hard. So in the first one, it's just a pathway of the light ray in the prism. So here it can't be answer number one because the light ray is moving away from the norm. It's like it's going there upwards. It's usually light ray is faced towards the base. So that's like a usual concept. So here, if you look at this, it's going uh, the rays, the arrows of these rays, one is faced in this direction, the other one is faced in other direction, and then so this second one is wrong. The third one, that's the right answer. It's like a normal scenario. The fourth one, uh, so here in this question, they are asking to show the light ray at minimum deviation. Wait a minute. They're saying to show the light ray at minimum deviation. So earlier in the previous slide, I think I missed a point. If you all had noticed, I've written it on the slide, but I didn't talk about it. So this point here, if it is an equilateral triangle, then the refracted ray is parallel to the base at minimum deviation. So anyone like if you know an equilateral triangle, all the angles are equal, all the sides are equal. At this point, the refracted ray is parallel to the base of that particular triangle. So that's the concept used here. So according to that, the one that is parallel to the base is going to be either option 2 or option 1. Did you understand that how 2 or 1 should be the answer? Because it's like, but this is not an equilateral triangle, but yeah. Okay, so that's for equilateral triangle. I missed that point, but it's not relevant to this question. So equilateral triangle, if the refracted ray at minimum deviation is parallel to the base. But in this is not an equilateral triangle, so you can eliminate 1 and 2. So it can't be parallel. So it's most likely the answer is 3, but we can see why 4 is wrong. 4 is wrong because uh, it moves along the surface. This is like what do you call critical angle, and here it's total internal reflection. So answer here is 3. Question 2, you can try question 2. It's actually not hard. So the ray of light incident on face AB, normal to it. Normal to it means the path it's moving along the normal and then it hits the surface. When it hits the surface, when it moves along the normal and hits the surface, we know R1 plus R2 is equal to A. But here R1 will be equal to 0 because there is no refracted angle. That means R2 is going to have the value of 40 degrees. If R2 has the value of 40 degrees, if R2 has the value of 40 degrees, then we can say that the incident angle at this particular point is going to be 40 degrees. And then they say the ray emerges through the face AC grazing it. Grazing it means it's like going along the surface. Now we know if it moves along the surface, then the angle of incidence is going to be equal to the critical angle. So here, NA, if you say N refractive index of glass is equal to sine value of angle of incidence there, it's going to be 40 degrees. It's equal to refractive index of air into sine 90. So here sine 90 and A is going to be equal, it's 1. Sine 90 is 1 and A is 1. So refractive index of glass is equal to 1 over sine 40. Did you all understand that? Let me know if you understood it. The second one. Did you understand? If so, I can move on to the next part. You want me to explain the second part again? Okay. So, now they're saying the ray of light is incident on face AB of prism normal to it. When it's normal, it's traveling along the normal and it's perpendicular, so there is no deviation at the first surface. So there is no refracted angle at that surface. And then it reaches the second surface and they are saying the ray emerges through the face AC, grazing it. So grazing it means it moves along it. So if it is to move along it, we know that it moves at a 90-degree angle. If this moves along the surface, we learned earlier about critical angle, where when it is when the incident angle is I and refracted ray moves along the boundary, this incident angle is called the critical angle. So in here, the incident angle in this case is the critical angle. So we know from the equation we learned earlier, R1 plus R2 is equal to A. A is 40. It's given in the question. So R1, it doesn't have a value. So R1 is 0, which means R2 is directly 40 degrees. So if R2 is 40 degrees, that means this incident angle is 40 degrees, which is also the critical angle, which is 40 degrees. Then you have the equation that we mentioned earlier. N1 sine I is equal to N2 sine R. So here the refractive index of glass is the N1 value because that's the incident one. Sine I value is sine C, which is also sine 40, which is equal to N2, which is air. N2, the refractive index of air is 1. Sine value, sine 90. Sine 90, the value is again 1. So sine 90 is 1. So Ng sine 40, you can write Ng for refractive index of glass is 1 over sine 40. So that is the first answer there. So did you understand now? So this thing, it's mainly focusing on critical angle, and that part I just skipped that part and came here because you all wanted prisms and water droplet. And yeah, okay. So before we draw a ray, we should draw, I have to draw normal, right, for circle. For triangle, it's perpendicular to the surface. So let's say for triangle, the normal is going to be always perpendicular to the surface, always 90 degrees with the surface. Did you understand? The normal is always 90 degrees to the surface at the point where the ray knocks on that surface. Okay, well understood. So I'll move on to the next one. So this is all questions. Maybe you can try these questions later. I'll just move to the theory since. Okay, so this one, I think you all know this from O-levels also, where when a white light ray hits the prism, it splits into its 7 colors. And as I said earlier, violet has the highest deviation, meaning more than the original path than the other colors, it moves away. So violet has the highest deviation. There actually has been a question about that also. So which one has the highest deviation? So that is basically the one that's here. And then moving on. Okay. So next part is right angled isosceles triangle. So this is it's there in your resource book as well. This the image on your right is the image that I got from your resource book. So as I mentioned earlier, critical angle of glass is 42 degrees Celsius. So critical angle of glass, so CEG, let's say 42 degrees Celsius. So when let's say, so in a right angle isosceles triangle, so right angle and then isosceles means these two sides are equal, which means these two angles are also equal, like the oral concepts. So right angle isosceles triangle. So if there is a light ray that enters along the normal, so let's say normal is the line that is perpendicular to the surface, right? So you asked earlier also, the normal for a prism is perpendicular to a particular surface. So then when you draw the line, the normal, and if the light rays enter along the normal, it doesn't have any reflection or it doesn't get refracted to any direction, it just moves along the path and then it reaches a point of incidence. Now we know if it total when it reflects inwards, we know this angle is 90, which means 45-degree angle is the angle of incidence. So I is equal to 45. So since incident angle here is equal to 45 degrees, we know that the critical angle of glass is 42 degrees. So incident angle in this case is greater than critical angle of glass, which means that total internal reflection takes place. So here it's total internally reflected. So total internal reflection takes place and the ray moves back into the same medium at the same angle as the angle of incidence. Yeah. Okay, so it's 12 also. Good morning, people. Uh, so it'll be the same angle. So that is the concept of this isosceles triangle. So even in the second example, so when it comes as an incident ray, since it's 45, 45 is larger than 42, which is the critical angle. So total internal reflection takes place. And then again, here also incident angle 45, because it's 45 and it is greater than 42, again total internal reflection takes place. So this is what happens inside the isosceles prism, like right angle isosceles prism, if and only if the ray enters along the normal. If it enters like in some direction, let's say it entered like this, then this thing won't happen. So it's only if it enters along the normal. So that is regarding this part here. So yeah, so that is it. And one more thing. So here they are given these arrows showing the object. So this is the tip of the object. You can follow this arrow and then you can mark the tip of that same object, like the direction is the same. So if this is the bottom of this arrow, along that ray only the bottom is formed in the other side. So if you're seeing an image, it's like according to this ray, the direction of the ray. So it won't switch. Did you all understand this? About right angle isosceles triangle. Okay. Then about this picture here. This one I found it somewhere else, not in the resource book. So this is one instance where the light ray it enters like this and then it goes refracts and then total internal reflection again refraction it moves like that, like that, like that, like that. So usually they give this part of your ray diagram, this part of your ray diagram, and then it's in the old questions mainly. I haven't seen any recent questions like this, so it can be asked. So they give an empty box and they'll be like, what can come here? Or what is the direction of the prism that can come here? So if you know this, you can easily identify. So one thing you should notice in this double arrow here, which is in the top at the beginning, goes to the end, goes to the bottom at the end. So there is one other instance like in lenses and stuff where this switches. So you have to know this clearly because sometimes they can give that and then give the option as convex lens or something like that, and then you get confused. So you should know it clearly. Then I think there's one more part. Okay. So this is the last part on prisms. So ignore the top images that is related to some other topic, which I didn't, I mean, I gave you all a slight idea on it, but it's not in the syllabus also. It's just I included it so that the session won't be boring, but in the end, we didn't even get to do it. So, okay. So for emergent ray to exist, we need the refracted angle should be less than critical angle. So we know this is the R value, the incident angle at this surface. If R is greater than critical angle, we know that total internal reflection takes place. If R is equal to critical angle, it moves along the boundary. So if R is less than critical angle, it moves outside. So it refracts. So for refraction to take place and for this emergent ray to exist, this critical angle should refracted angle should be less than critical angle. So that is the point here. It's not a big point, but yeah, just letting you know because you have to be clear about the concept. Did you understand that point? And then there's just one other point. That's all. So if you understand, let me know. Okay. So I'll move on to the next one, next point, last point. So if the incident ray is along the boundary, and it gets refracted, we know that angle here is going to be the critical angle because this is 90. So it's perpendicular 90 degrees. It's perpendicular. So this angle right here is going to be the critical angle. So if that is the critical angle, it goes hits this boundary, and let's say again it goes along the boundary after it hits the surface, then this is 90 again. If this is 90 again, this R2 will also be equal to critical angle. So this is one instance where there are two critical angles, which means both the refracted angles are critical angles. So R1 plus R2 is equal to A. Now we know R1 plus R2 is equal to C, which means 2C is equal to A. Did you understand this one? Okay, so that's it on prisms and water droplets. So, so that's it for this. So these were all supposed to be done, but it's my first session today and first time teaching. So there were some issues. So yeah, okay. So you can let me know your feedbacks maybe tomorrow. I mean, it's already tomorrow, so you can send a message about how you felt about the session. And yeah, thank you for joining. And good night. Assalamu alaikum. Also, if you all need anything, you can let me uh, know. Like, send me a message or something. If you all need anything, if you all want to know anything. Okay, then. Okay, based on 2027 paper being hard, basically everyone says their own paper is hard, so it depends. I thought my paper was hard. The people thought their paper was hard. So yeah, based on that, I think 2027 means you can go along with the theory. Like while you're studying your lessons in class, maybe you might be already following a class. So with that itself, you can do revise your theory after the lesson. Make a short note. Do the past paper questions related to it. And if you have any other lesson that you missed or like you didn't do the past paper questions, since you're 2027, you have time. So you can revise that as well, like along with this. So you can do those earlier lessons as well, like past paper questions. But don't forget about practicals. MCQ is not everything. There's practicals and there is also essay questions. So most people skip out essay, but essay is important. You have, I think, PSU essay books that you can do all the essays in that. 2027, you have enough time. So I personally did all the essays in the PSL book, I think twice. Depending on the lesson, I did twice. And I think not only MCQs, even the essays matter because for me, I think I scored much better in my part 2 paper than my MCQ. So I was more confident in my part 2 paper than my MCQ, and that's like a main reason because MCQ was a bit difficult for me. I don't know about the others. Anything else you want to know? I think you can unmute and speak because there is only me and only the two of us if you want to. Okay. So you don't need anything else. So I can end the meeting.